Today is the last class in this semester, and I want to continue the discussion about the magnetic properties of solid and wrap up everything by today. All right? Don't forget, we are going to have a final on the day after tomorrow, 13th, okay? Now, the ferromagnetism, okay? The ferromagnetism is it's a complex of ferro and anti-ferro. In other words, the exchange energy and of this system has two ways: the parallel uncoupled, unpaired spin. Unpaired spin is important. And then one of the ferromagnetic materials, one of the nature is that the exchange energy get low when the unpaired spins, nearest unpaired spins have oriented parallel, then the exchange energy can get low. That is the ferromagnetic properties. And at the same time, the anti-ferromagnetism is anti-ferromagnetism also exists in this material. So it's a little bit complicated, but the main advantage of this ferromagnetism is that it's an insulator, okay? So in high frequency device, the ferromagnetic material has to be used instead of a ferromagnetic materials, okay? So it in terms of the industry, it is very, very important. Let me give you the examples of ferromagnetism, and then one is spinel structure. It is very much related to the crystal orientation, crystal structure, I should say. And one of these ferromagnetic materials is the spinel structure. And another system is inverted spinel structure. And we can see some of the materials which is going to be called intermediate spinel. And also it does have a mixed ferrite. The normal spinel structure, the example of this is a zinc ferrite. When you say ferrite means Fe3O4, okay? So zinc ferrite means ZnFe3O4, something like that, okay? Inverted, let me give you the example of this. Inverted spinel, the Fe ferrite, nickel ferrite, and cobalt ferrite. all these ferrite materials show inverted spinel. And the intermediate spinel, mangan and magnesium ferrite. Mixed spinel, mixed ferrite, nickel, zinc ferrite. Okay, when we say nickel zinc ferrite, it means that we have a mixture of nickel ferrite and zinc ferrite, something like that, okay? And in order to understand the magnetism in these ferrites is that we have to think about the crystal structure. For example, the spinel structure means that if it has a formula like this, we are constructing the FCC with X, okay? So per unit cell, we have 4 atoms in this unit cell, okay? And then it takes the 1/8 of the tetrahedral site. Tetrahedral site. And B2, it takes 1/2 of octahedral site. Hedral site in this FCC crystal structure. If you look into the FCC crystal structure, now it is a 4 FCC on the top view. We have atoms here and then at the bottom and the top, something like that, okay? That is the FCC. And here we have a half, at the half height we have atoms here, and in total we have 4 atoms per cell, right? And the tetrahedral site, we have 1, 2, 3, 4, 5, 6, 7, 8 at the 1/4 and 3/4. So we have 8 tetrahedral site. For the octahedral site, we have at the center and at each corners we have a octahedral site. So as a total 3 plus 1, that is a 4 octahedral site per cell, okay? And then it has 2 because the half of the octahedral site is occupied, and we just have 1 A atom in a cell because 1/8 of a tetrahedral site is occupied in this structure. Okay, that is a normal spinel structure. Okay, and this octahedral site atoms is anti-parallel, anti-ferromagnetic, which means there is 2 B atoms, and then these B atoms has an exchange energy lowest when their unpaired spin becomes anti-parallel. Okay, so this normal spinel structure, the A is the only source for the magnetization because B, it shows anti-parallel arrangement. Okay, so for example, zinc ferrite. Zinc, it does not have any magnetic properties. Zinc plus 2 does not have any unpaired spin. So as a total, zinc ferrite, it does not show any magnetic moment. Okay? So the zinc ferrite is used for the mixed ferrites. By itself, alone, zinc ferrite does not show any magnetization, but when this zinc ferrite is mixed with the nickel ferrite to form a mixed ferrites, then it does show it has an effect in the total magnetization. So zinc ferrite, even though the magnetic moment is zero, but it is very useful to form a ferrite. Now, for the inverted spinel, for example, let me give you the example of a nickel ferrite. Okay, in a nickel ferrite, the inverted, it is called inverted because nickel Fe, Fe. The oxygen is not going to do anything, so the formula is actually Fe2O3, something like that. It can be written something like this. Okay, it forms the crystal structure with this chemical formula. But when you are talking about the magnetic properties of this, you don't have to consider the oxygen atoms because it does not show any moment, magnetic moment. So when you write down this thing in this manner, then in a normal spinel structure case, this will occupy the tetrahedral site, and these two should have taken the octahedral site. That is a normal spinel case. But this material is the inverted spinel, is called the inverted spinel structure because this first Fe takes the tetrahedral site. Okay? And then the nickel, which is supposed to take the tetrahedral site in a normal spinel structure, will take the octahedral site in this inverted spinel. And then this two is octahedral site. Octahedral site. It occupies the octahedral site. Okay, that is going to be called inverted spinel. Now, let me see this in this inverted spinel, the nickel ferrite. Okay, the Fe has 5 unpaired spins, so Fe 3 plus ions will have 5 Bohr magneton. Okay, and this Fe and this Fe supposed to be antiparallel, and it's supposed to show antiferromagnetism. Okay, so the magnetic moment of this Fe and this Fe is going to be canceled. So net in this material, it has nickel 2 plus, which is a 2 Bohr magneton. So the net of this nickel ferrite shows the magnetic moment of 2. Okay? Now, let's see what happens if we mix that nickel ferrite plus 0.1 10% atomic percent of zinc ferrite. what happens if we make a mixed ferrite, something like this? We know nickel ferrite has two Bohr magnetons, okay, from this calculation. It shows the inverted spinel. And zinc ferrite, this is a normal spinel structure, so that the magnetic moment is 0. Right? Now let's see what's going to happen if we mix those two things. And in the normal way of thinking, this material should have two Bohr magnetons, right? But it turns out that we are going to have more than two Bohr magnetons if we mix a nickel ferrite with zinc ferrite, just 10%. Okay, nickel ferrite, as I mentioned here, the Fe and octahedral site, we have Fe, something like this. This is the tetrahedral, this is the octahedral site, right? And then it does have a 0.9 atoms in here in this mixed structure. And in this zinc ferrite, we know the zinc is in the tetrahedral site, and then we have octahedral site. We have a ion in the octahedral site, something like this, because it is a normal spinel structure, and then we have just a 0.1 of this in this mixture. Now, in a tetrahedral site, tetrahedral site. I'm just making a class like in a high school, isn't it? In a tetrahedral site, we have Fe, 0.9 Fe, 0.9 Fe, and then here, the tetrahedral site, we have a zinc, 0.1 zinc here, and then octahedral site, in this mixed ferrite, we have a 0.9 nickel plus 0.9 Fe plus octahedral site 0.2 Fe. Okay, here the 0.1 and 0.1, so 0.2 Fe, something like this. And then this 0.9 Fe and 0.9 Fe will show the antiparallel ferromagnetism, so that it's going to be null. And then zinc, it does not have any magnetic moment by itself. So in the total, we have a 0.9 nickel plus 0.2 Fe. And then nickel has a 2 Bohr magneton, and Fe has 5 Bohr magneton. So in total, we're going to have 2.8, isn't it? 2.8 Bohr magneton. Now this 2.8 is bigger than the 2 Bohr magneton here, which means if we mix the nickel ferrite, which has a Bohr magneton 2 Bohr magneton as a magnetic moment, with the zero magnetic materials, zinc ferrite 0.1 or 10% in atomic percent, then we end up with 2.8 Bohr magneton, which is bigger than the pure nickel ferrite. Now you can see the usage of this zinc ferrite, right? Okay, that is the survey of magnetic moment. Magnetism. We start with the two inherent magnetism of the materials, which means every material has this two magnetism in itself. One is diamagnetism and paramagnetism. And then we move to the spontaneous magnetization phenomenon, and then we survey ferromagnetism and anti-ferromagnetism, and then finally we talk about the ferrites, ferrimagnetism. Okay. Now that is the survey of the magnetism in magnetic materials. Now the rest of this chapter has to deal with some ferromagnetic domains. When we say ferromagnetic magnetism, it means that the unpaired spin spontaneously align themselves in parallel to lower the exchange energies. So if that happens in the ferromagnetic materials, then by nature, if we give the materials enough time, then the magnetic materials should have all one direction alignment, so that it should show very, very high magnetic moment. But that's not going to happen in the reality. What's going to happen is that, like poly crystals in the crystal, in terms of the crystal structure, when we talk about the polycrystals, we're going to say the same thing happens in the ferromagnetic materials. That is domain, magnetic domain. Okay, that is certainly different from the grain boundaries, of course, in the materials. This magnetic domain means the unpaired spin in one direction, and in the same material, it does have different directions, something like this. So this is totally different from the grain boundaries. These magnetic domains can grow. One domain can overcome the other grains, domains, with the external magnetic field. It can move. The domain boundaries can move. Okay. So the net magnetization in ferromagnetic materials, which is spontaneously magnetized, can be zero in a normal case. But when we apply the magnetic field to this material, ferromagnetic materials, then one of the domains favored, so that the grain, the size of differently oriented domains have a different size, then it can have net magnetic moment. So from now, what you are going to talk is that how this domain size can be determined, how this domain orientation, one orientation of each domain can be determined, things like that. What kind of energies is going to be applied to make a stable domain size and domain orientation and things like that. So in order to understand that, we have to think many energy states, and then the materials take the optimum, the lowest energy, which means the lowest energies, then to determine the grain size, domain size and domain orientation. And the energies we have to take into account in the domain determination. The first, we have exchange energy, And secondly, magnetostatic energy. And then magnetocrystalline energy. And block wall energy. And finally, we have a magnetostrictive energy. Okay, exchange energy. This exchange energy is, we have talked about this exchange energies. Exchange energies, by definition, is kind of an energy, it's a driving force. We can say this is a driving force for spontaneous magnetization. Right? So this exchange energy actually want to make a big domain size. You want to make the domain size bigger. Static energy is the energy which can be expressed as the external electric field, a magnetic field, and dV in a total volume. So the magnetic static energy if we have domain boundaries in the ferromagnetic materials like this, let's see. Let me start with this. If we have a magnetic domain like this, then the external magnetic field is going to be formed something like this, okay? And then that magnetostatic energy is the integration of this magnetic field over the volume, okay? So in order to lower down the magnetostatic energy, this material tend to have this closed loop of this magnetic field, something like this. Okay? Then we can minimize the magnetostatic energies. All right, magnetocrystalline energy is the magnetic energies incorporated with the crystal structure. So in every magnetic materials, if it is a single crystal, it has an easy direction and hard direction for the magnetization. In other words, if 1, 0, 0 directions, the magnetic poles can be easily aligned in 1, 0, 0, but it is very hard for the magnetic materials to align in 1, 1, 1 directions. So magnetocrystalline anisotropy energy, it can be said magnetic interaction between the magnetic dipole and crystal orientation, crystal structure. Okay? Plug wall energy is a domain wall energies. Is a domain wall energies. If we plot the domain wall width with the energies, the exchange energy, if we have a bigger domain wall. What is a domain wall? domain wall is if this domain has orientation like this, and if this domain wall has orientation like this, and if we talk about domain wall, it means that inside this domain wall, the orientation of the magnetic field is going to be rotate something like this, okay, inside this domain wall. So the energy related with the domain wall, the exchange energy is going to be decreased exponentially. This is the exchange energy. Because domain wall becomes big. Why? Because the misorientation between the nearest neighbors is going to be slow if we have a domain wall, big domain wall, okay? And then the energy, exchange energy itself can be lowered. But the magnetocrystalline anisotropic energy is going to linearly increase, okay, as the domain wall increase. Because the hard direction, we have a large number of hard direction spins if we have a widened domain wall. So this is an anisotropic energy. Magnetocrystalline energy is linearly related. So in total, the energy related with the domain wall now is going to be something like this, okay? And then it goes like that. So it has a minimum energy somehow in the middle of this domain wall width, and this is the most stable domain wall width. So domain block wall energy is a compromise between the crystalline anisotropy energy and the exchange energies. All right? Magnetostrictive energy is a physical volume change with magnetization. Okay? So in this magnetostrictive energy, you can see that if you have a magnetic materials with this big domain boundaries, then with the magnetization, it does have a volume change with the magnetization, something like this. And this magnetostrictive energy, if the material has a large magnetostrictive energies, which means it has a big change in the volume, then it has a tendency to break down this magnetic domains into small domains, something like that. And in this case, with the magnetization, it does have a small change in the volume, so that it can sacrifice the less amount of magnetostrictive energies by break down the magnetic domains. As you can see, these 5 energies is going to be in a struggle to make the total magnetic energies the lowest. And then in that sense, the magnetic domain size is going to be determined, and the orientation is going to be determined, and the magnetic domain wall size, wall width is going to be determined in the ferromagnetic materials. Okay, that is a survey of that. And finally, we have to talk about the hysteresis. In the diamagnetism and paramagnetism case, we don't have to talk about the hysteresis of the material, because these materials only magnetize only when there is an external magnetic field. In the paramagnetism. In diamagnetism, it does have inherent magnetic moment in itself. But in ferromagnetic materials, you have to talk about the hysteresis, the magnetic magnetization curve. In magnetization curve, if you draw the magnetization curve in this system, you have a magnetic moment and the magnetic field, something like this. And then originally, at first, it shows the zero because of this, the confliction of those 5 magnetic energies. And then it is going to be magnetized something like this in any fashion. And then when it demagnetizes, it shows us something like this. And then when it is going to be magnetized, and then it is going to go this end and this end, and it's going to be repeated in this cycle. We call this a hysteresis. All right? And then this is the saturation magnetic moment of these ferromagnetic materials. This material cannot have more than this magnetization. And then this is going to be called a saturation magnetic field, the magnetic field necessary to saturate that ferromagnetic material. And then this is a remnant magnetization, which means if we get away the magnetic field in this material, it does have the magnetic moment something like this. These values without the magnetic, any magnetic field. And this is going to be called the coercive magnetic field, which means if you want to take away all the magnetic moment in this ferromagnetic materials, you have to apply this reverse magnetic field to demagnetize the materials. And then we call this coercive magnetic field. It's just the kind of thing that you have to cover in your high school stuff, right? Well, we supposed to have as an application, we don't have to talk about the hard magnets and the soft magnets. That's all the applications, and we don't really have to know the basic fundamental reason for that phenomenon, the hard magnet and soft magnet. But as an application, recently we have studied the GMR, giant magneto resistance. That is a magneto resistance. And then we have another application of this. There's a random access memory, bubble magnetic bubble memory. All right? But the concept of the GMR and the MRAM has been developed about decades ago, but real application has been not that popular these days. Even though some researchers still working on the GMR and MRAM because of its high advantage in the device, in terms of the device. So if you are interested in this applications, you may go for the reference to find it out. Okay, that's all I prepared for this class. And then we are going to have a final on the day after tomorrow, 13th, in this class. And then the examination is about 2 hours, but I don't think the questions are difficult. It's very normal, and the questions are mainly focused on the last chapter, chapter 9, electrical properties of the semiconductors. Okay? All right. Have any questions? I think it's the last chance for you guys to ask questions. You never raise the questions in the class. But I enjoy the class, and then I especially enjoy the class with the small students in the class. And everything has been recorded on YouTube. So I think students can have the information on these lectures at home. Okay, I'll see you the day after tomorrow then, in the exam. Thank you.